so we left off in the middle of section 2.1 last time. And we had gotten to a question that I sort of backed out of, and I wanted to look at it with you again, number 7 here. We were talking about domain and range, and I'd like to actually start from the perspective of an equation here, since we hadn't actually done that, and then we'll talk about the graph, which is where I was jumping to, probably a little too excitedly last time, as we moved our way through. So as we're looking at this one, what I'd like for you to recognize is that you do have an equation. None of the ones we had done before did we have an equation to actually consider. We had graphs, we had lists of ordered pairs, but we did not have an equation. So if we're taking a look at this from an equation standpoint, because sometimes you are given an equation, and you can graph it, and that's okay, we will in a moment, but I want you to think about it from an algebraic standpoint first. So on this one, we have a square root, and when we take a square root of any value that doesn't have a plus or minus in front of it, it's just the square root. Anytime we take a square root of a value, we only get positive numbers out of it, right? If I were to ask you what's the square root of 25, you would tell me 5. Now don't tell me any negative numbers, right? It's 5. So this is an understood, it's actually called the principal square root when we see it like that. It's understood to mean that all those values, which are representative of the y values, are bigger than 0. Okay? Every value that we get out of the square root is bigger than 0. If we're working, which we are when we're talking about graphs and domain and range and so forth, within the real number system, so we're working in the real number system, it also means that what we see happening underneath the radical can't be negative. Because if it's negative, it gives me imaginary values, not real values. So I need what's underneath the radical, namely the 5 minus x, to also be greater than or equal to 0. So the output comes out as greater than or equal to 0. But I also need everything that's the input, not just the x, but everything underneath that's the input of the radical to be greater than or equal to 0. So we're going to solve this inequality. We did this back in 1.7. So we subtract our 5 from both sides. So negative x is greater than or equal to negative 5. And as we divide by negative 1, what do we need to remember?
Flip the sign.
Yep, flip the sign to be less than or equal to. And negative 5 divided by negative 1 would be 5. So that's my domain because it's telling me my x values. It says that I need values smaller than 5. Well, that would be negative infinity to 5. I can't get any bigger than 5, but I can equal it, so I have a bracket, and I'll have a parenthesis in front of the negative infinity. Now going back over for range to the y values, the range starts out at values that are supposed to be bigger than 0. So 0 is my smallest, and I can equal it, and I go up from there. It's 0 to infinity. Here's what the graph should have looked like last time when I started going too quickly. If you put this into your calculator, the graph actually looks like this. So, if you're thinking about this from the graphical perspective that we considered last time, x values, I can start from the very far left until I get to 5. That's my domain. That's negative infinity to 5. Y values, I'm climbing up a ladder. I start seeing values at the y equals 0 mark, or the x-axis, and I continue to see y values up forever, so it's from 0 to infinity, and that's my range from a graphical perspective as well.
You said something like when you're climbing up, or the y, when you're looking for y values, you look left to right.
Yes. As you're climbing up the y-axis, you're looking left and right. As you're walking along the x-axis, you're looking up and down. Exactly.
So, like, if you were looking for y, you would just say negative infinity to 5, right? Because it's left to right.
If you're climbing up the y-axis, you're looking from left to right. Okay, so here I am. Whoa, I want to draw him better. Here I am climbing up the y-axis, right? And the first place I see values is right here. And the last place I see values is that I go up forever seeing values. I'm still reporting y values. So I'm reporting from 0 to infinity along the y-axis. Okay. All right, changing gears slightly inside of this section, we're going to talk about function notation. Function notation allows for several things. One is that when we see this notation right here, it's equivalent to saying y. Okay, so it's telling me the y values. This notation is often used as f, parentheses, x, close parentheses, and it's read as f of x. Parentheses in mathematics are probably the most used thing. I don't know why. We use them to mean lots of things. Sometimes we use the parentheses to set pieces apart for grouping symbols. Sometimes we use parentheses to mean multiplication. Sometimes we use parentheses to indicate that we've got ordered pairs. Sometimes we use parentheses to indicate that we've got an interval notation. And now we also have parentheses here indicating function notation. The context should tell you what the parentheses are doing, but it doesn't make it necessarily always straightforward to remember that there's multiple uses for the parentheses. We are not using them here for multiplication. That's usually the confusion at this point. All that notation means is the y value, but it also gives you the added information that you do in fact have a function. Right? If I just give you the equation y equals x squared here, you don't know that you have a function from the get-go. But if I give you the notation g of x equals x squared, you do know it's a function from the get-go. Now, that's not really why we're using it here that's the most helpful. The most helpful reason to use it here is because it simplifies questions. So if I were to give you y equals x squared, and I wanted you to find the y value, what is y when x equals 2? And that's the notations, all the notation I had was our regular y equals notation. I'd have to write all of that down. I mean, like that's what I'd have to actually ask you inside of a question. If I have function notation, all I have to say is g of 2. And it means the same thing as all of this stuff written down. It's an abbreviation of notation. We like abbreviations of notation in mathematics. That's actually where exponents come from. It's where multiplication comes from. Multiplication comes from the idea of repeatedly adding something. What is 5 plus 5 plus 5 plus 5 plus 5? If you don't want to write it all out, you write it as 5 times something, right? What is 2 times 2 times 2 times 2 times 2 a whole bunch of times? Well, if you don't want to write it all out, you write it as 2 to a power. Okay, so this is another one of those shorthand notational kinds of things. So instead of writing all out, what is y when x equals 2, I can write g of 2. And what you see happening notationally is that the 2 is replacing the x in the notation, which means that the 2 will also replace the x on the right-hand side in the equation. And what is 2 squared? It's 4. We can use that notation whether it's positive or negative, right? So here, the negative 2 is now replacing the x in the notation, so the negative 2 replaces the x in the equation. Negative 2 squared is also 4. It's negative 2 times negative 2. So it's a notational shortcut. It works for other equations too. So you can see on number 9, the equation is 3x squared minus x. One of the big differences you'll notice between 9 and 8 is that the x is there in the equation twice instead of just once. All that means for us is that when I do the replacement, I replace every x with the value. Again, I'm using the number 2 here. So when I replace the x with 2, there are 2 places to replace the x with 2. So I have 3 times 2 squared minus 2. Please remember order of operations. That was the very first question on your last test, involved order of operations. So as you're looking at this, you have 3 times 2 squared minus 2. Don't subtract before you multiply. Don't multiply before you do the exponent. Those sorts of things. Order of operations will continue to apply forevermore. So when we're looking at this particular expression, we will start with the x squared part, which was the 2 squared now. 2 squared is 4. So now I have 3 times 4 minus 2. 3 times 4 is 12, and 12 minus 2 is 10. There's also a tendency, and I noticed it especially on the redos, not as much on the original attempt, maybe just because you didn't have as much work shown out on your original attempts. But on the redos, I noticed sort of an overuse on some of your papers of equal signs. Some of you like to put equals, equals, equals between lots of things that are not actually equal. So as you look back at the comments that I made, if that's you, you'll know it, because I made a comment that says you can't use equal signs like these. Okay, equals does not mean and my next step is, and my next step is, and my next step is. Equals means it's taking two quantities and you're saying that they're equal to one another. Now, you'll notice on this particular problem, I've got more than two, I've got equals in there multiple times. But again, between every two pieces, they're all equal. Every single one of them are equal to the one before. That's the only way to use the equal signs in a way that's appropriate. The second part here on number 9, and it looks kind of funny. It doesn't have a number, it has a W, right? I mean, so what am I supposed to do with a W? Well, you do the same thing. It just means that you aren't going to simplify your answer to a single number. You replace the X with W. So in place of the X, you put a W here. In place of the X, you put a W here. But the reality is that all of that notationally isn't really needing those parentheses any longer, right? So as I sort of clean this up, I will rewrite it as 3W squared minus W. You might look at that and be like, so I just wrote W's instead of X's. Why does it matter? Well, we're going to use this notation here in just a moment. But what I want you to recognize is I don't have to evaluate something at a number. I can evaluate it at anything. So, I mean, I could ask you, what is f of star? You could replace the w's or the x's all with stars. It's f star squared minus star. I mean, like you can do that, or 3 stars squared minus star. Doesn't matter what it is. Okay, so we're going to use that idea here in a moment as we look at the last topic in this section, which is actually called the difference quotient. A difference quotient is actually defined as f of x plus h minus f of x over h. What a difference quotient is it's a slope. So one of the ways that you have seen written your slope notation is y2 minus y1 over x2 minus x1. I'll remind you that these are just y values that we're subtracting on top. It's function notation, but they're y values that are being subtracted on top. And they're being subtracted for the inputs of x plus h and x. And if you were to take x plus h minus x, you'd get h. So on the denominator, you're really subtracting x values. It's kind of hidden within the notation, but it really is just a slope. So you might be looking at that and saying, well, but why? Why change the notation and make it look all funny like that? It's actually used further on in mathematics, which I know not all of you are going to be taking the class that further on uses this component. But that's kind of how mathematics works, right? You build upon it in lower courses, so those that do use those later on have seen it before. So that's why it's showing up, is because it's a component in a later course. Specifically, you see it in calculus for sure. Sometimes you see it in a pre-calc or a trig course as well, but definitely by the time you get to calculus. So that's what this is sort of a precursor for. I teach this a little bit differently than your book does. So if you like what the book does better, that's fine. You can do what it does. I like this better because I think it breaks it down into smaller pieces that makes it more manageable. So what I'm going to teach you is something that's called the 3-step process. So we're going to do this in 3 steps. The first step that we're going to do is we're going to find f of x plus h. And you'll notice that that's just this first component of the expression. What is x plus h when I plug it in for f, into f? Okay, so my equation is over here. I have x in there 2 times. So there are 2 places that I'm going to put in x plus h. So I have 3 parenthesis x plus h squared minus x plus h, it's plus 7. Okay, so the first thing I'm doing is simply rewriting all the x's as x plus h. It's really important to remember that you cannot distribute squares. You cannot do this with a square. You can do it with multiplication, you cannot do it with squaring. So what do you have to do? You actually have to multiply it by itself. So you end up rewriting this as x plus h times x plus h. You are welcome and encouraged at this point to go ahead and distribute the negative through, because that's multiplication, it's a negative 1. So that would end up giving me negative x and negative h, and then I still have my positive 7 at the end. Okay, are we okay so far? All right. You can multiply the 3 through first if you want. You know, it would just be 3 through this, and then you'd multiply that result by the next piece. That's okay. I don't usually do that in that order. I usually multiply the 2 pieces that are identical, the binomial pieces, together first. So I'm going to save the multiplying by 3 till the end. So if I multiply the first terms together, x times x is x squared. The outer term is xh, which is exactly the same as the inner term, xh. So I have xh plus xh, which is 2xh. And then the last term is h squared. And I rewrite all the pieces. Every step is should to be equal to the step before. So many of you have a tendency to just sort of leave off the part you're not currently working with and work with some other stuff and then throw back on the part that you were working with before to the stuff you left off. It's not how it's supposed to work. If I put a equal sign, it should mean that the next step is equal to the previous step, which means I include all the pieces, whether I'm currently doing anything with them or not. Our last step, I'm sorry, I did leave off a parenthesis. My apologies. Let me put that in there. After that h squared, there was a parenthesis. My last step within this step 1 is to distribute the 3 through. So I'll multiply my 3 through that parentheses to each of the terms, giving me 3x squared plus 6xh plus 3h squared. And I do still have the negative x, negative h, and 7. All of that is f of x plus h. So if on a problem like this over here, you were simply asked to find f of x plus h, you would be done. Our problem's asking us to do more than that. It's asking us to find a difference quotient. So we've done the first step of the 3 steps. Step number 2 is f of x plus h minus f of x. In other words, it's the entire numerator. So step 1 was the first piece of the numerator. Step 2 is the entire numerator. What do you think step 3 is going to be? Divide by h, because that's all that's left, right? That's step 3. So I'm going to take what I just found in step 1 and I'm going to rewrite it. 3x squared plus 6xh plus 3h squared minus x minus h plus 7. And I'm going to subtract off f of x. Well, that was what was given to me right here. It's 3x squared minus x plus 7. Now you have a couple options. One option is that you could, in fact, distribute the negative through here. That's fine. If you'd like to do it that way, go for it. The reality is that everything that's currently in that set of parentheses has a counterpart in the other part of my problem already. So notice, 3x squared is here, and 3x squared is here. And I've got a subtraction sign on the second one. Those are going to cancel, aren't they? So I don't usually multiply the negative through. I just do the cancellation step. The next one, negative x here has a negative x here. And the second one, I'm subtracting it off, making it a positive. So those also are going to cancel each other. And then the last piece, the positive 7 has a positive 7 here, but it's subtracting off the second positive 7. So again, those also are going to cancel each other. All those components that are in that parenthesis at the end are eliminated. So it starts to feel like the first step I did, that I labeled as step 1, is sort of this expansion step. I expand things out. I have a lot of pieces. Step 2 is a condensing step. It eliminates most of the pieces from step 1. So what is left? Well, let's find them. We have a 6xh. I have a 3h squared, and I have a negative h. Those are the only pieces that are left. So I'm going to write them down. I have 6xh plus 3h squared and negative h. If I did it right, everything should have an h in it. So it's good that we see that it does, right? If at this point you look at it and you're like, oh dear, there's something that doesn't have an h in it, you've got a mistake that you made somewhere. So that's the end of step 2. Step 3 is the divide by h step. So we take step 2, 6xh plus 3h squared minus h, and we divide by h. Now, you guys did a much better job on your redo attempt than on the original attempt at not doing this. But some of you like to cancel out the denominator with just one piece of the numerator. That's not possible. The only time cancellation can occur is either if it's in factored form, right? You see multiplication pieces in the numerator, which we don't have here. Or if you see that every term in the numerator has the piece of the denominator you're wishing to cancel. And they do here, right? I have an h in every single piece of my numerator. So I am allowed to do the cancellation as long as I cancel it with every piece of the numerator. You have to remember, cancellation like this is really division. So as you divide things out, they don't disappear completely, but they do divide to the number 1. So if I have 6xh and I divide by h, it's 6x. And if I have 3h squared and I divide by h, it's still 3h, because only one of the h's canceled. And if I have the negative h at the end divided by h, it's negative 1. It's really easy to lose that last h especially, because there's nothing else visibly attached to it. But when you divide it, you get the number 1, and it was negative. So this is the resulting piece of your difference quotient after all 3 steps. What your book does is it puts all 3 steps in there from the very beginning, and you have to simplify everything all at once. I think it's easier to break it apart. Yes, ma'am?
If the last h was positive, would you have to write +1?
Yes, you would. You're right. And it could be. It very well could be. It also could be that the last h had 3h in it. So when h is canceled, you're still left with the number 3. We're not always left with the number 1 or negative 1, but we sometimes are. Any other questions on that one? So we most definitely are going to practice another one then before we quit this section. So I'd like for us to go through that same process again for a new equation. Our new equation this time is x squared minus x plus 3. It does have the name g of x, so within my 3 steps, I will call them g of x plus h. If you inadvertently use f on it every single time, I'm not going to complain. It's not a big deal. It's just a different name. So step 1 is g of x plus h. It means I replace the x everywhere with x plus h. So I have x plus h squared minus x plus h, and then I have plus 3. Okay, again, you cannot distribute squares. Squaring a binomial means multiplying it by itself. So it's x plus h times x plus h. At some point, so we might as well do it now, you're going to distribute the negative through the second piece. It's multiplication. That's why you get to distribute it. It's not an exponent. So negative x and negative h plus 3. All right, now, the parts that are in parentheses still are going to be multiplied, FOILed out, or distributed out. X times x is x squared. The outside is xh, the inside is xh. Xh plus xh is 2xh. The last term, h squared. And I have negative x, negative h, and positive 3. That's it for step 1. It's actually a little shorter than step 1 over here because step 1 over here had a 3 on the outside and we simply don't have a coefficient on the outside this time. Okay, so step 2 is the entire numerator. So it's the same g of x plus h I already had minus g of x. So we've got that x squared plus 2xh plus h squared minus x minus h and plus 3. And then we have to subtract off the original equation we were given, which was x squared minus x plus 3. Again, if you would like to distribute the negative through, you can. It's not wrong. I just don't go through the worry of doing so because I know everything in that parentheses is going to have a part that it cancels with. So I just do the cancellation directly. The x squared and the x squared are going to cancel. The negative x and the negative x are going to cancel. And the 3 and the 3 are going to cancel. So that leaves me with 2xh, h squared, and negative h. So I have 2xh plus h squared and negative h. Step 3 is to divide by h. So 2xh plus h squared minus h divided by h. Okay, each of the pieces in the numerator are separated with addition and subtraction. They're not multiplication. So in order for the denominator to cancel with the numerator, it has to cancel with every single term. An alternate way you can think about it is, could I factor an h out of everything in the numerator and write it at the front? Right, like common factor kind of thing, and leave that piece with the h in the denominator and cancel the h factor with the h in the denominator. And you could do it that way too if you'd like that. I'm going to go ahead and continue with looking at it piecewise since we did that before. This h will cancel with this h as long as we have an h here and the h here, leaving us with, again, it happens to be a negative 1 at the end. It could be a different number, but it was still negative 1. So 2xh divided by h is 2x. H squared divided by h is h. And negative h divided by h is negative 1. So our difference quotient ends up as 2x plus h minus 1. Any questions on that? All right.